Start the recording. So good morning, everyone. We shall start now the session of Professor Nicole. Professor Nicole, he is a professor at University of College London and Hertford. London, Metropolitan and Oxford, you have a lot of visiting positions. He is an internationally known for his work in human thermal comfort, principally the adaptive approach, and with Professors Michael and Susan Rove, and co-author of the leading books and chapters on the subject, such as adaptive thermal control, principle and practice, and adaptive thermal comfort, foundation and analysis. Also, he is a co-author of numerous journal articles and author and other publications, including the comfort chapter in CIBSE Guide A. I would like to welcome him and welcome all the attendees. Dr. Now we are give us a session with the title, The Shapes of Thermal Comfort. It's a very interesting topic, Dr. Nicole. So please welcome him, and please, Dr. Nicole, you have the floor now.
How do I control are you going to put on the...
Would like me to present the PowerPoint for you?
Well, I'm not quite sure how. I've got it at home, but I just wondered what was the best way to do it.
If you have it on your PC, you can just go to the icon on the bottom. It's called Share Screen. And Yeah, and you click on it, and then you click the presentation that you want to share.
Right.
Yeah, it's now sharing. We can see.
I'm at the end of it.
Yeah. Okay, you can go to the start.
Okay.
Okay.
So now just...
And I would like to remind all attendees that at the end of the session, please, if you want to ask Dr. Nicole any question, please write it in the Q&A, and I'm going to forward these questions to him. Thank you.
Well, I'd like to... Can you hear me?
Yes, I can hear you very clearly.
The idea of looking at the shape in thermal comfort, which may seem a rather strange idea in itself, because we don't think of comfort as having a shape, is that nevertheless it's always been a way in which people try to represent what is actually a very complex issue. It started with scientific models which used the theory of physics and physiology to show how you can make an index of comfort, how people are able to have been able to do it in terms of a graphical presentation. Well, this is one of the early ones. This is a corrected effective temperature. It's a nomogram, what's called a nomogram. And here we have two sort of shapes. One of which is for people who have a normally clothed, one clo, which is normal in European societies, or half a clo, which is relatively less clothing. And the way this works is that this is what's called a nomogram. And the way it works is you can calculate the CATE, or you can do it by using a graphical approach. So that, for instance, in this case, we have this is to get it a bit closer. What you do is you've got the dry bulb temperature down this side and the wet bulb temperature down this side. I'll explain what those are in a minute. And then you have the air velocity. Now, each of these lines is a different air velocity. And so if we have a situation where you have a dry bulb temperature of 30 and a wet bulb temperature of 20, what you do is you join the line, the 30 on the dry bulb side to the 20 on the wet bulb side, and then you say, well, what air velocity have we got? We've got 1 meter per second. And what that means is that the CET, or the corrected effective temperature, is shown by where that intersects with a 1 meter per second line on the nomogram. This is a method. What it is showing how the physiology can be explained by looking at the situation these people are in, where they've got 30 and 20 for dry bulb and wet bulb, and air velocity. So it allows you to calculate the CET. And these were very popular, these type of things. If you look in, if you go to the PLIA website and you download the note Thermal Comfort, written by Zoccoli, you'll find that he has a number of these nomograms, which were seen to symbolize or concretize the calculation and make it easier, not doing it mathematically, but doing it using a graphical method. Adjusting, for those of you who are not familiar with the sort of measurements that were made in those days, this is a wet bulb, this is a Sling Hygrometer. And what you did is you held it by the handle and you swing it round. And you have two thermometers here. One of them has a wet sort of sock around it. This is the container for the water, and it would wet this wick. And what you would get, obviously, is the one with a wet wick, because the air because it cools the air. You get generally a lower value for the wet bulb temperature than you do for the dry bulb temperature. The other thing that you had to measure was the air velocity, and this is the thing that was generally used in those days. It was called a CATE thermometer, and what you did was you heated up the bulb. You see there are two lines here. You heated up the bulb of the CATE thermometer. You hung it up, and you saw how long it took to get from one mark to the other mark, and from that you could calculate the air velocity. In some ways, a better way than some of the instruments used nowadays, because this is more like a person. I mean, it's a bulb. You're not cool. Air velocity changes terribly quickly. And what this did was to smooth that out over a period while it was cooling down. Anyway, to carry on with the subject we're here to talk about. I've gone to the end, dearie me. Start at the beginning again. Sorry, I'm not very used to. The other graphical representation was the well-known comfort zone of Olgay. Again, he was doing it in terms of the dry bulb temperature and the relative humidity. These were the things he saw as important. And what he was trying to do was to show how there's a zone in the middle of the temperature range, generally between 20 and 30. and this is designed for hot climates. So 20 to 30 was the sort of area where people were used to being comfortable. And if they find themselves outside that area, they would have to provide some air movement above. So if you found yourself at this temperature, you would have to provide a meter per second of air velocity. If you were below it, then you'd need some radiation, maybe solar radiation, maybe heat from an electric fire or something like that. So those were the ways of representing comfort. And this is more for architects than for physiologists. It was just a diagram. But it was very widely used. This is for tropical comfort zone, as you can see. Where's my thing gone? Anyway, those indices were basically trying to derive an index which you could use to represent the way that people felt, the way that people felt about the climate. Now, an alternative method, which is the one that we've generally used, is to do a comfort survey. You just go around a number of people, you ask them how they feel, you measure the temperatures, you measure the humidity. I expect most of you will have some experience of this, but you can measure all sorts of things, but there'll always be some that you don't. For instance, did you measure the outdoor weather? And how did you measure the outdoor weather? Did you measure the posture of the subjects? Were they sitting down and cuddling themselves, or were they were they standing upright with their arms out and so on? So it's those sorts of things that may seem sometimes transitory, but the problem is that we're talking about an attitude of mind. The attitude of mind is affected by these things. It's not just a physiological phenomenon. It's the way that people feel about their environment, as well as what the things that you can measure, the temperatures and so on. And this is a fairly normal sort of comfort survey. You ask people how they feel, whether they would prefer to feel warmer or cooler, and so on. You'd find out what clothing they're wearing in order to be able to put that into your measurements. You should also notice whether they've used controls. I mean, here they have the blinds down, a bit of window open, and then you measure the environment. You measure probably the temperatures, the dry temperature and the globe temperature. You measure the air velocity. You might measure other things like the light level or the noise level, and those sorts of things which might affect, if you wanted to find out whether they affected the way people felt. And what we're going to do is to look at what the results from these surveys tell us about the people who are being measured. So these are the sort of subjective things you might ask. Whether they feel hot, warm, slightly warm. This is the ASHRAE way. You can also measure. You can they're generally represented by a number, so that you can do a statistical analysis. What you want, according to the normal experience, is what you want is at what temperature or humidity or whatever people feel neutral, so that that's considered the sort of the perfect environment, or whether you're slightly warmer or cooler, or whether you're warmer or cooler in a way that might make you feel uncomfortable. And also you could ask whether they would prefer to feel cooler. You notice here that I've put cooler as a positive here, because this is very difficult to be sure, but on the whole, if people are hot, they want to be cooler. And so that scale will generally be in the opposite direction to this scale here. And another one which I'm going to use later on is skin moisture. Whether they have no skin moisture, slight skin moisture, moderate, or profuse. So those are things that tell you something about the physiological state of the person, whether they're having to sweat. And this is some data that we collected in the UK. It's collected in Aberdeen in Scotland, which is really to the very north of the UK, and in Oxford in England, which is sort of central south of England. And we had 16 subjects, of whom 6 were in Scotland and 10 were in England. And what this graph shows, according to the scale on the right-hand side, is the comfort vote. This is so that 1 is cold, 2 is cold, 6 and 7 are hot, and all the rest in the middle are either neutral or slightly warm or cool. And you can see that on the whole, as you'd expect, the hot ones, the triangles, are on the top part of it, and the circles, the little black circles, are on the bottom part. But you do see some triangles down on the bottom part and some circles up in the top part. This is an indication of the complexity of thermal comfort, that it's not precise. A lot of the work that's been done is to try and find a precise description of a really rather vague shape. And the other thing I'd like you to notice is that there's a lot of talk of what do they call it? These things where they go along and then they start going up. Anyways, at about 15 degrees, this is in the UK, at 15 degrees outdoor temperature, which is the one. The outdoor temperature is along the bottom here, and this is the indoor temperature. Above 15 degrees, the indoor temperature tends to start rising as the outdoor temperature increases. And below 15 degrees, the temperature is, this is the low S regression line, is more or less horizontal. Now, what we want to do really is to find out why that happens. And we can do that by doing some graphs. Here, this is the air-conditioned buildings. These other things are naturally ventilated buildings. The air-conditioned buildings, firstly, the range of temperatures is relatively small. It's about 5 degrees between the upper edge and the lower edge of this cloud of points. But in the naturally ventilated buildings, the thing goes along horizontal and then starts to rise up. And if you see whether the heating is on in the naturally ventilated buildings, these are buildings which in the winter will generally be heated. You'll see that the 15 degrees is where it stops being a heated building and starts being a free running building. The fans are used at different times, generally more in the higher temperatures, obviously, and the windows are opened more in the higher temperatures. Don't open the window in the cold weather, but you do in the warm weather. So what people have done is they've taken the building. If it's air conditioned, they don't need to do anything. But if there's got a naturally ventilated building, they need to make some changes to use the adaptive opportunities they have, the fans, the windows, and the heating, to make the indoor temperature suitable for what they want. And what you find is that the range of temperatures, if you take the outdoor temperature and you find the range of temperatures that are found comfortable in the air-conditioned buildings, is quite narrow. In the naturally ventilated buildings, the range of indoor temperatures is much larger. It's about twice as much. And there is no precise relationship. If you do these surveys, you'll find no precise relationship between temperature of a space and the thermal sensation. This is the comfort vote here on the vertical thing, and along the bottom is the indoor operative temperature. And you can see that although the regression gives you a very precise line and apparently very small variation in possible the possible comfort votes for any indoor temperature, actually you find that the thing is very much less precise than that. That you can have people who are much too hot at 24 degrees, and you can have people who are much too cold at 24 degrees. Further up, the cold votes reduce, and as the temperature goes down, the number of hot votes reduces. So you do get a relationship, but it's a much vaguer relationship than is often implied by the use of regression analysis. Here's some data from, this is the second survey. I'm going to show the results from 3 surveys we've done. This is the second survey done in Europe, and it was called SCATS because it was done for a project called, anyway, I can't remember it now. Anyway, it's a long time ago. But what's interesting is that this is a much wider range of outdoor temperatures, going from about -5 to up to about 30, 35, 37. And whereas in the UK data, sorry, I should have pointed this out. Oh God, no, what have I done? the range here in the UK was about -2 to +25, whereas in the whole of Europe, we get a much wider range of. I should have left the, I should have asked somebody else to do this bit. So so the temperatures go down further and they go up. The countries that were used in these surveys were France, Portugal, Sweden, the UK, and Greece. I've not put the Greek data in because the Greek surveys were only carried out for part of the year, and I wanted to show the whole what happens over a whole year. But what you do see is this kink at 15 degrees, which seems to apply to in the whole of Europe as well as just in the UK. And what you also find is that data from different countries shows different shapes. Now, I don't think this is necessarily because the people in France are different to the people in England, but I think certainly the buildings that were chosen by each of these surveys was done by a different university, and they chose they were supposed to choose 5 buildings, which they went to do a survey every month. And you can see in France there's a sort of strange gap between 10 and 20 degrees or 10 and 15 degrees, but you can see that below 15 degrees, the temperature is a bit vague, but generally horizontal. Whereas above 15 degrees, the indoor temperatures are going up in concert with the outdoor temperature. As indoor temperature goes up, as the outdoor temperature goes up, the indoor temperatures go up as well. Portugal is a bit different. Here, the whole range of temperatures, even below 15, the whole range of temperatures is changing with the outdoor temperature. Indoor temperatures changing generally, but very much less precisely than the French ones. It's generally changing in a way that we would expect in a building which was either not heated or only heated in very cold weather. You might say that below 15, you've got no evidence that it's horizontal or still going down, but generally the shape of the cloud here is much the same as in a naturally ventilated building. In Sweden, all the buildings were air conditioned, and you can see that the Swedish indoor temperatures are between 20 and 25, like the air conditioned buildings in the UK, between 20 and 25, right up to 30 degrees. And right down to -5. So that the Swedish ones are sort of typical of a highly controlled indoor environment. And the UK ones are really a bit of a mix-up. I'm not quite sure. I think there's a bit of a kink here, but it's not very obvious. So that what we've got is different types of buildings were looked at by different groups of researchers. Now I want to show to bring in Pakistan. Now Pakistan is almost like it has a very wide range of temperatures in Pakistan. We have a number of different sorry, I'm not, I'll put that one up there. You'll see 5 areas basically. One down here on the coast, labeled 1, is a coastal region, more or less similar to the climate that we have where we are now. The second one is Multan, which is a hot desert. Yeah, low-lying hot desert. The Punjab in this sort of area, extending into to India, obviously. Then in 3 we have a cold desert, which is a high altitude. This here is Afghanistan, and the equator is on the same sort of mountainous area that Afghanistan is. Then in area 4 we have a composite climate, which is a bit of hot and a bit of wet, and then in area 5 we have a mountain climate, Sadi Sharif. We're getting into the foothills of the Himalayas here, and so that the temperatures tend to be lower. And here you can see on this multiple graph over here, Karachi, you can see the temperature is remaining relatively stable, still varying quite a bit between one part of the year and another, between a bit under 20 to a bit over 30. But nevertheless, compared to the other areas, it's much it varies much less, and that's because of the influence of the Indian Ocean. And then there's the other 4 areas which I've characterized by particular cities. Multan, the hot desert, which is the highest one here, going up to 35, 40 in the summer. These are average temperatures, so you must remember that there'll be within a day, there'll be a variation about that. Then Peshawar or Islamabad are the sort of composite climate. Then Quetta, which still gets quite cool in the winter, and reasonably. Sorry, Quetta is this. I'm getting confused here. The hottest one, Multan, is this one, and then Peshawar, then Sadu Sharif. It's in the foothills of the Himalayas, so it's doesn't really get very cold in the winter, but it's nevertheless it's cooler than the neighbouring areas. And then the coldest is Quetta, which is the one in the southern mountains. Now, what we did here was each of those areas, we got a group of researchers, generally from a local university or somebody like that. We got a group of researchers to go out every month, take the temperatures. Unfortunately, the Pakistani Met office wasn't able to give us the variation in the temperature during the day. So this is the average temperature for that day. So the outdoor temperature is the average outdoor temperature. And for each of these cities, you can see Multan up the top there, and Saidu and Quetta going right down. I think most of these were offices in Pakistan, and this was in the 90s, and very few of them had air conditioning. And so it's almost like natural ventilation. So this is what would happen if you didn't have any heating or cooling. There's probably a bit of heating in this part of the Quetta data. But generally, there's no heating or cooling. But every office has a fan. So fans are, and obviously an opening window. So the fans are in every, you can assume that every office had a fan. And you can see that the data I've collected, that Karachi is slightly less because there was a problem with security for the students going out and doing the measurements. So there's a problem for part of the year. So Karachi is rather underrepresented, but you can see that it is there. Karachi, you can see it's here and going across, and obviously on the whole, a flatter curve than the other ones. What I've done here is to try and sort of make a cloud for each. There's Multan going right up and into the mid-30s outdoor temperature, and indoor temperatures going almost up to 40. This is Saidu Sharif, which is a bit cooler. And then this is Quetta, which extends from a much lower top temperature. You can see that the data from different parts has a slightly different cloud, and that's because of the difference in climate. And if we look at whether the people are comfortable or not, you can see that red is hot. So there's a lot of hot people at this end, and blue is cold, and there are a lot of cold people down this end. But nevertheless, the temperature, the indoor temperature, ranges from 10 to something like 40. I think that's probably a bit of an exceptional situation, but I know obviously there were some people who got to well over 40. But generally, the people above about 30 degrees begin to get warm. This is the actual percentage, which looks less than you expect from, but it means that something like 20% of the time, the total population, 20% of the time is either cold or hot, uncomfortable, probably we could say. Whereas the other 60% of the time, they're comfortable. So although the temperatures go up and down quite, although the comfort votes appear to be a lot here, I think the red is the way the computer program lays it out. It does the last things for on the top, so it overestimates the amount of heating. And if this is if you take all the data, this is an estimate of the number of people, the number of people uncomfortable, the proportion of people. So up until a relatively large number of people uncomfortable up to about 20 degrees. This is over the whole of Pakistan. But only less than 20% are uncomfortable. The 20% is a sort of taken by ASHRAE as if you've got 20%, that it's acceptable to have 20% of people uncomfortable. And you can see that there are between about 20 and 35 over the whole of Pakistan. There are less than 20% uncomfortable. If you take just Multan, which is the red one, they're fewer than 20%. Sorry, I've made a sort of an attempt to show that the high level of comfort or the low level of discomfort is at a higher temperature than for Saidu Sharif, where that's the round dots. Saidu Sharif, the people are comfortable at a lower temperature than in Multan. So behind this overall thing, there are a number of other specific things for different parts of the country. I mean, we can use this data to look at Olgay's comfort zone. This was Olgay's comfort zone. I've tried to line up so that the temperatures are more or less at the same. And between 20 and 30, he said people could be comfortable. The data we have here suggests that people can be comfortable. A lot of people can be comfortable quite a way outside that, up to 35 degrees. There are still quite a lot of people who are comfortable. And at the bottom, Olgay was saying 20 degrees. In fact, people can be comfortable down much closer to 10 degrees or 15 degrees. So it suggests that it doesn't suggest that Olgay was wrong. It suggests that he was being cautious, because people found ways of making themselves comfortable, maybe by running a fan, maybe by other means, wearing more clothes and that sort of thing. So what this graph shows is where people have got the fan on. The fan is on above 30 degrees. So Olgay wasn't wrong. He just was a bit conservative, maybe. The other thing is, actually, we found that we did calculations as to how much of the change of comfort temperature was due to clothing. And we found that actually in the summer, people are wearing this sort of shalwar kameez. These are bank workers in Saidu Sharif. In the winter, they're wearing more clothes, thicker clothes, and wearing hats and so on to keep themselves warm, so that they overcame the temperature. They could be comfortable at a wide range of temperatures. And I noticed that the posture is different. It's much more open posture in the summer than there is in the winter. And this shows the number of garments being worn at different times. The blue ones are the people with relatively few clothes, relatively light clothing, should we say. And the dark brown ones are the ones with wearing a lot a lot of layers of clothing. And the other two graphs, sorry, the other two graphs, this one is the average clothing insulation. This is in clo units, so it's 1 clo, 2 clo, and you can see that in Pakistan anyway, there's when you're in a work situation, there's a minimum level of clothing which is accepted almost by everybody, so that you can't get below about half a clo. You won't get below half a clo, but you can get you get amounts of clothing right up to an average of something like 2 clo. This shows the number of this is the 3 layers, 4 layers, 5 layers, 6 layers, 7 layers. So you can see that 4 layers is the usual. This is the use of windows. 73% were closed and 27% were open. They do open windows, but not as much as you might think. At the very highest temperatures, the only advantage of opening the window is to increase the air velocity. So it's not as much as there are quite a number of people who keep their windows closed, even in the hottest weather. And we can look at different things. We've looked mainly at the indoor versus the outdoor temperatures, but you can use the same. What we've got really is a 2-dimensional graph with a 3rd dimension added by the color or shape of those points. And so we've got globe temperature versus water vapor pressure. And this you can see is more or less like the shape of a psychrometric chart. We can do clothing versus indoor temperature. You can see the clothing goes up. That's one we've shown you before. This is a clothing insulation versus water vapor pressure. And you can see the profuse sweating that really only occurs when the clothing insulation is small. The higher the clothing insulation, people are either unaware or have ways of dealing with skin moisture. And this one here, this is globe temperature versus air velocity, and you can see that the air velocity suddenly starts to increase at 30 degrees. And that's because probably most of the air velocity is due to fans. So people are switching on fans at roughly 25 to 30 degrees. And the profuse sweating really only occurs at the very high temperatures. And just as an interesting thing, this is a picture which shows that you see the 2 lines here. These are the extent of the cloud of Pakistan that we've been looking at. What I've done is I've put in the points for Portugal. If you remember, Portugal was varying as if it was naturally ventilated in the same way as the Pakistan. And you can see that the Portuguese data falls almost entirely in the within the Pakistan. Pakistan, the temperature variation at any one time can be as much as 15 degrees, but it's smaller in Portugal, but it's within the same area. So an outdoor temperature of 15 to 20, 10 to 25 is giving the same indoor temperature in Portugal, or a similar range of temperatures in indoor temperatures. Sorry, for as the Pakistan. So that's the data from Portugal. And actually, if we look at the data as we've seen from a number of other surveys, this is from another paper that I wrote, which shows the clouds, the temperature clouds for different parts of the world. This is Tokyo, Pakistan. These are Melbourne and Darwin, Shanghai. I think Shanghai, I can't be sure whether these are free running buildings. Shanghai, I can't be absolutely sure that they're all free running, but nevertheless, with Melbourne, England, Darwin, Pakistan, Tokyo, you can see that the way that the indoor temperature varies with the outdoor temperature in those, because it's largely governed by the building they're in.
Excuse me, Professor Nicole. You have got like 5 minutes to go.
Yeah. No, I'm just
sorry about this.
No worries. So I've got to the conclusions now anyway. The relationship between subjects in two climatically similar places, there is an underlying order among free-running buildings. However, the difference in comfort shown between different cities, Pakistan, and other parts of the world, so this is based on climate rather than country. So, well, I mean, all the things we do it by country. I think we need to think of it in terms of climate and not in terms of country. The shapes of thermal comfort, clearly not decided by the indoor environment, just by the indoor environment, but also by the climate, the culture, and the context. By the outdoor environment. The presentation of the data from a survey as a cloud can help understand the precision of the interrelationships. These are relationships which we're used to seeing a regression line and thinking this is really precise and so on. There's no variation from one to another, or there's a 2-degree variation or something like that. In fact, we need to look at the actual cloud of points to see whether it works. And I think this approach of looking at the clouds produced by
excuse me, Professor Nicole, you are muted. Please unmute.
Sorry. The cloud becomes an analysis tool to give us a more realistic impression of what the relationships are than using high-level statistics and that sort of thing. Anyway, thank you for your attention. And I don't know, you may know that there's a network of people who are interested in comfort. And if you want to get our, whenever somebody writes to us saying there's a job available here, or we need a researcher here, there, we send it out to all the members. So if you want us to add your name and email to the network, you can write to me at this address. Thank you.
Thank you so much, Professor Nicole, for this wonderful, insightful lecture. And for the time limitation, we will go through the questions and answers part. So we have here a question from Dr. Najjar. Thank you, Dr. Fergus, for the wonderful presentation. May I ask about what metrics used for indoor air velocity? I know ADPI, but not sure if better metrics can be used. This is the first question.
For the indoor air velocity?
Yes.
Well, I'm not quite sure what you're asking. I don't have a particular metric for indoor air velocity. It's just the air velocity, you know, meters per second or feet per minute, depending on when you're doing it. But I don't really don't have any metric for it. I suppose we have on occasion tended to use the square root of the air velocity, which is more equivalent to its cooling power than the air velocity itself, but that's all.
Okay, thank you for that. Another question from Caroline. Professor, why did you represent the indoor temperature as a globe temperature instead of operative temperature in the charts? Thank you very much for your presentation.
You can't measure operative temperature. Operative temperature is a theoretical temperature. It's not a real temperature. But you can, the nearest thing you can do to measuring it is the globe temperature. It's a problem. I mean, you know, operative temperature is a theoretical temperature which tries to mimic the effect of different parts of the air, the air temperature and the radiant temperature particularly. And the globe temperature does it, the globe temperature does it as near as we can, just for a measurement. That's where I say globe temperature. In theory, we could easily put operative temperature, but it's what we can measure is the operative is the globe temperature, and we just use it as a similar. It has a similar. I don't know. It behaves in a similar way to what we would expect the operative temperature to. So if you're doing an experiment, you can't measure the operative temperature. You can only measure the globe temperature or the air temperature and the radiant temperature and put them together. See what I mean?
Thank you. The last and final question from M. Indraganti. I hope that I'm spelling it right. So the question is, if you were to conduct the Pakistan studies today, would be seeing similar comfort temperatures from the offices there? Is there any temporal dimension to the comfort temperature in a region?
I think the difference now, I don't know. I think the fact that we only had 1 or 2 offices in the mid-90s which had air conditioning is, I suspect, and that was I think it's partly because we were working with office workers. There were a few people like shopkeepers and those sorts of things, but those sorts of relatively stable. So nowadays, when I think the problem was, I mean, we had one of our Pakistani colleagues said his parents had air conditioning in their house, but they could only use it for 2 months of the year because energy was so expensive that they couldn't afford to have it running all the time. Now, I don't know whether that's changed. It may well have done, but I think the change will have been not in the people themselves, but in the sort of adaptive opportunities that they have. It may be that more of them have air conditioning, more of them have heating, and those sorts of things.
Okay.
I think probably nowadays you would find fewer people were at the ends of the comfort scale and more people in the middle. I don't know.
Okay, that's right. Okay, so the final one, I hope that about from Pratival Lamsal. So he was asking about the time duration of thermal comfort survey in Pakistan. Time duration.
In Pakistan,
yes,
it went for about a year. We wanted to have every weather. I mean, one of the things that we learned is because, you know, we looking from Europe, we think of Pakistan as a very cold country. One of the things that we really learned was that there are almost as many, sorry, a very hot country. And one of the things we learned was that it can be cold as well as hot. That actually, you know, the weather is very variable. And an enormous range of different temperatures. And the amazing thing was that people deal with these despite that.
okay, great, thank you. Thank you so much. That was the last question. And I would like to thank you very much for this insightful lecture, and I hope that all of us just enjoy it as I am. Thank you, Professor Nicole. And unfortunately, we have to end the session now. Thank you so much for your attendance.
Well, thank you. When I was asked to speak, and you said I had to speak for an hour, I never thought that I would speak for nearly an hour. So,
so yes.
Thank you for being very kind to me.
Thank you so much, Professor, and see you all.